record. Okay, I think it's recording. And hopefully Zoom will tell me a location it's stored at. So it is recording. That said, this is gonna be like a 90-minute record. I think it's gonna get pretty boring. So I will record the lectures, but if you have any suggestions of maybe something that you will actually watch afterward, let me know, because I just, at least from my perspective, if somebody tells me to watch a 90-minute lecture record, I'm not going to watch it. So okay, good. But good suggestions. Okay, and I guess I'll be able to see a chat with them. Okay, so I'm going to turn off my laptop webcam so I can share screen of my whiteboard, my tablet whiteboard. There is going to be a slide. So the lecture notes are still on Laulima, so you don't have to write if you don't want. Where's my pen? Okay, I lost my Apple Pencil. But anyway, yeah, you don't have to write it. You can just download the finished lecture notes on Laulima. But you can follow along. There is going to be there does appear to be a slight delay between what I write and when it appears on the screen. But okay, but I'll look for, I might try a different tablet on Wednesday. Okay, good. So I'll turn off this thing. No, not end meeting. Can I just turn it off? Can I just turn you off? I see. So I actually have two. Can you hear me now?
We can hear you now.
Is it loud or is it garbled? Because
it seems like it's loud enough now.
Okay, I'm not quite sure if it's using the mic on my headphone or if it's using the mic on my tablet. That's my only concern, because I'm very confused by this being a host and being a co-host. Okay. Anyway, so we'll continue on with particle filters, right, or importance sampling. And of course, they start doing the long. Sorry, let me close the window. Okay, I can hear the lawnmower. I don't know if you can hear the lawnmower. Okay, but basically the idea is we're still kind of in the domain of common filters, which is where we're still, I mean, we're going away from it, but what we have is the state space model, right? State. Right, so we have some dynamic model. And then some observation model. Right. And so the usual assumption, so X is the state, which is hidden and now observable. How do I point to it? X is the state, which is hidden but not observable. And Y is the observation that we have, right? So, and then also we assume that when we have these models, we always have some sort of state noise and some sort of observation noise. Usually these are Gaussian, but not all the time. So the assumption for common filters is that this function, the dynamics of the state, is a linear function, right? So what you will see is it will be some matrix times the state, right? And also the assumption is that the observation is also a linear function. So we can write it as some matrix times the state again. So right, so that's the assumption we make with Kalman filters. And the idea of Kalman filters is, again, we start over time 0, and we're going to keep seeing new observations, right? And then so we're going to go from our estimate of what the state should be at time n, given observation up to time n minus 1, to our estimate of the state at time n, given all the observation up to time n, and then we're going to keep iterating, right, and go and so forth. Right. So this, in Kalman filter parlance, this is the predicted estimate. And the filter estimate. So what happens is that Kalman did the math for us. So, I mean, it's not, a one-line equation, but the Kalman filter has, you have the algorithm, and you can implement the algorithm. But basically, the algorithm gives you equations to compute the predicted estimate and also the filtered estimate, right? So it's closed form equation. But the problem with the issue with Kalman filter is nice and closed form, but we have to assume both a linear dynamic and a linear observation model, right? So, but what we want to do is, we know in the real world, very few things, real systems are actually linear. So what we assume is we're going to go to nonlinearity. So now these are general functions which are nonlinear. And idea is that we're still doing the minimum, the least mean square estimate. So still doing the LMS. Which is what the Kalman filter is. So the Kalman filter is an LMS estimate, except it's for a linear model. But in general, the LMS estimate is the conditional expectation. So it's the expected value of x given y. Right. So the expected value of state given observation. And we know that the equation for conditional expectation, of course, is, your in continuous time or in continuous space, in discrete space, right? But basically, regardless of whether you're really using the PDF or the CD or the PMF, you need, these are called the posterior distribution. Okay. So if the posterior distribution is really, if this thing is really complicated, or if the summation is really large, or the integration is, of course, large, then it's very difficult to compute this thing directly from these equations, right? So imagine if you have to sum over like 10,000, like 2 to the 10,000 terms, or 2 to the 5,000 terms. It's very difficult to sum over this. So basically, you want the conditional expectation, but it's very difficult to compute it. Even if you know what this conditional probability is, this might still be a very difficult thing to calculate. So then the method is, rather than computing it using, rather than using these mathematical equations, what we can do is we can use Monte Carlo methods. So in fact, Monte Carlo methods are used to compute complex integration expectation. They're used to describe complex probability distributions. Right. So the whole idea of Monte Carlo method is based on sampling. So the idea is that if we can generate enough samples, so suppose I'm trying to generate a number between -1 and +1, right? So the first time I generate the value, it could be here, second time here, 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 right? Basically, I can generate different values. Sorry, the x doesn't really, right? I could generate all these different points. So they're meant to be a 1D thing. So it's meant to be a value between +1 and -1. But eventually you see that, you know, depending on the shape, the probability distribution, the values I generate, you see there's more concentrated around 0 than a +1 and -1. So what I'm doing here is I'm actually generating, it will give me an approximate of a Gaussian centered at 0, right? So if I want to find the expected value of this probability distribution, this Gaussian distribution, then I can just take the average of all these points, and you can see that the average of all these points should be something close to 0, right? So basically, if I can generate the samples from these posterior distributions, right, the probability of the state given the observation, then I should be able to, I can take the average over many samples, oops, and I should be able to find the conditional expectation, which is also going to be my LMS estimate. So I should be able to basically compute what is the best estimate for, what is this estimate for the state at time n, given all the past observations, right? If I can compute this conditional expectation. The downside is, unfortunately, in many cases where we cannot, if we cannot compute the conditional expectation, it means that we're actually working with a fairly complicated probability distribution. It means the posterior distribution is complicated. So it's actually going to be very hard to generate samples from this distribution. So again, if the distribution is like a Gaussian or uniform or exponential or Poisson, this doesn't matter. It's no problem, right? We can just open up MATLAB, and there's all these functions built in to generate samples. But most of the time, it's going to be something weird. Like if the posterior PDF looks something like this, you can't generate samples easily directly from this. Right. So that's why last time I introduced this idea of importance sampling. So importance sampling is a way to compute basically expectations, right? So these expectations or conditional expectations, right? Basically, it's not just the expected value of x, it's the expected value of some function of x. So this also includes the variance, the second moment, and so forth, right? So you can also compute out the conditional expected variance, conditional expected second moment, and so forth, right? But the idea of the importance sampling is we don't sample directly from this distribution we care about, which is the conditional distribution, but sample from, so this is also called the target distribution. But we sample from a simpler distribution. Q. A simpler distribution Q. So for example, here, instead of sampling from this complicated PDF, we could just sample from a Gaussian, right? We could just sample from this. So this could be Q, and this is P, right? So this simpler distribution that we're going to sample from, there's many names, so it can be called the proposal distribution, or it can be called the important distribution. Right. But basically what we learned last time is that, you know, with general, if you were to sample directly from P, if you want to compute the expected value of h of x of y, you just take the average. But here, if you do importance sampling and you're generating from Q, you have to take a weighted average. So each sample that you generate, so notation-wise, it looks like, so this is a sample, right? And we imagine we generate our total samples. So say, I don't know, 100,000 points from the Q distribution. So instead of just taking the average, what we have to do is we have to take the weighted average. Right. And the idea of this weight is, of course, to basically compensate for the fact that we're sampling from Q and not from P. Right. Okay, so today we're going to continue on. So recognize that, I mean, when we talk about, like when I first introduced importance sampling, this is just for a probability distribution. Right. This is like a basic idea from statistics, from probability. But today what we want to talk about is time series. Right, because the difference between common filter and, you know, general machine learning, like the stuff we're learning in this class, and you take a general machine learning class, is that, or at least, or even with regard to what we talked about in the beginning of class, is that now we're working with time series, right? So we have states which change in time, and we have observations, which is updated in time, right? So obviously when things have, you know, information in time, we assume that there's some relationship between the point, the value here, and then the value at the previous time, right? So it's not just it's not just a random variable, but now we're working with these. You could think of this as a random vector, or you could think of this as a random process. So we're working with this time series where each value is a random variable. Okay. Okay, also one thing, just to go back, sorry, to this idea of the importance sampling. So just notation, right? So the importance sampling, we know this thing, there's a weight, right? So just from a notation perspective, right, I'm summing up all of these samples. So instead of keeping this, ratio, I'm going to define a new variable, W, right? Oh, and also I need to normalize by all the WOs. So this is my estimate of X. Okay, so here the weight W is just the ratio between the true, so this could the target distribution and the important distribution. But because I do this, I have to have this denominator term, right? So if I want to get rid of this, what I want to do is I want to normalize the weights. And that way, so I don't have to worry about this denominator term. About this thing. Am I going too fast? Is it okay? Is the pace okay? Can you hear me?
Yeah, pace is good.
Okay, okay. So let me know if I'm going too fast. I'm looking at, okay, anyway. Okay. So basically, so I know that, so I have to generate all of these samples, right? And again, these samples could be scalar numbers or could be vectors. So associated with each sample is my weight. So what I want to do is I want to normalize so the normalized weight is the original weight divided by the sum of all the weights. Oops. Right. So you see that because when I normalize the weight, I divide by the sum of all the weights. When I go back to my estimate, I don't need this term, right? So I don't have to worry about this bottom denominator. So what that means is that when I find my expected value by taking the weighted average, I can just have my normalized weight, right? So this equation is for if you're using normalized weight, and this equation is if you're using the unnormalized weight. Right. So note that, you know, depending on you have different types of weights you can work with. Okay. So now we can talk about importance sampling for time series, right? Okay. So we have time, x1, x2, xn, and that's the state over time, and then this is the observation over time. So technically, since we're using a probabilistic framework, if I want to consider what's the probability of seeing this particular time series, right? Of seeing, like, say, or even y1 y2, yn. So if seeing, you know, 5, 2, -1, 10, whatever, then for me to actually be able to describe this thing probabilistically, I actually need to consider the joint probability of everything. Right. I actually really need to consider the probability of x1 being a particular value, the probability of x2 being a particular value, the probability of xn being a particular value. And similarly, if I want to talk about posteriors, I have to consider the probability of x1 up to xn being a certain value, given I observe y1, y2, all the way up to yn. Right. Right. So if I want to work with time series, I have to consider all of these things. So obviously, one thing that should go into your mind is that if the n is large, right? If n is like 50,000, this becomes a very difficult. These become very difficult probability distributions to work with. Okay. But basically, we can think of a particular time series, right, a particular value, as a sample from these sort of joint distributions. Right. So we're going to call this one of these things, one of these samples, as a trajectory. Just because sample is usually associated with just you know a sample from a particular probability distribution. Here we're actually considering a much more complicated probability distribution than just your normal Gaussian or exponential. So we're going to call a sample from this kind of distribution a trajectory, and it's also called a particle. So this is why we're working toward this thing called a particle filter. Right. So you can think of, you know, I have time series. So if I were able to generate samples from these complicated probability distributions, then what that means is I have a bunch of trajectory observations. Right. So again, this is like but basically, rather than sample being a point, a sample is a time series, right? So a trajectory. So same as with classic importance sampling, we cannot, it's not easy generate these trajectories directly from the posterior distribution given y1, y2. Right. We cannot directly generate this. Instead, what we can do is we generate from a simpler distribution and we can use importance sampling. So same idea, except now instead of having samples which are 1 point, each one of our samples is going to be a trajectory. So just a word on notation, right? So you see it's very painful to write this. So instead, what I'm going to do is it's going to be a shorthand, where if I write capital X subscript n, this is going to be a shorthand for x1 all the way up to xn. And capital Y n is a shorthand for y1 all the way up to yn. So probability of xn minus 1 given capital Yn minus 1 is the probability of going from x1 xn minus 1 given y1 yn. Right. So it's just to reduce notation of having to write this. Oops, having to write this. You write something shorter. Okay, so what we're going to do is we're going to generate a total of R trajectories from my easier proposal distribution. Right. Okay, so once if I can do this, then the computing, the expectation is the same. Right. I still find the unnormalized weight, except now the unnormalized weight has to have this time n attached to it, right? This is the weight of my variable up to time n, right? So that's why this new subscript appears. But this is just the ratio of the target distribution for the ith particle over the important distribution of the ith particle. Right. So this is the same as with importance sampling, except now we're instead of each sample, we're talking about a particular trajectory of a certain length, right, of length n. And we can still find the normalized weight by taking our unnormalized weight and summing over all the values. Right? And in that case, after that, then to compute any function, right, such as, so for example, the one we really want is the conditional expectation. Right, so this will fall into it. To compute this, what we can do is we can just take the average. And multiply, take the weighted average, right? Okay. So if R is large, this for sure will be closer to the true conditional expectation. There should be H here. Okay. Okay, so of course this idea, I think it's simple, but in practice there's many pitfalls. So one thing is that obviously in real life R cannot be infinite. It can be large. It cannot be infinite. So therefore this approximation may not be as good as you think. You'll get a number at the end by taking the average, but how close the value is to the true value, we don't really know. Or at least it's very difficult to have an idea of how far away you are from the true value. So what do you think are some other pitfalls that I might have with this method? So the idea is that I have some target distribution, right? Which is the P. but I can't sample from that. So I can sample from a, I can sample from an easier distribution, the proposal, the important distribution, which is my Q. So in order to, take into the account of the fact I'm not sampling from P, I'm sampling from Q, I do this weight. But what do you think could be a problem that I could run into? Any ideas?
Could it be the accuracy of the weights?
So assuming that, so one thing the reason why I do this ratio is a lot of the time, one reason I do this ratio is that a lot of the time, what I know about the distribution is up to a normalization constant. So making the assumption that somehow you know what P and Q is up to the normalization constant that makes them sum up to 1, the weight itself should not be a problem, right? You're just taking one number divided by another number. So for sure, if I know the P up to a normalization constant and Q up to a normalization constant, I should be able to compute the weight exactly. So it's not exactly in the weight. It's in a little bit before I do the weight. Right, so still remember that you're not generating samples from P, because I think it's very intuitive to everybody that if I want the expected value of P, I just take the average of my samples from P, right? That is intuitive to everyone. But I'm not generating samples from P, I'm generating samples from Q. So the only added thing you need to know is that now I have to take weighted average. But what do you think I could go wrong with this Monte Carlo method?
You'd either miss values that either aren't in your original P by sampling from Q. So say Q is too tight and you miss the left or right hand side, or the opposite and took a sample that has some reasonable value in Q but which wouldn't be in P at all.
Good, very good. Right, so exactly right. That's the reason is that, I mean, my knowledge of P is kind of shaky to begin with. I know it up to a normalization constant, but suppose it's really complicated. I barely know it. I pick a importance probability. I may have some idea as to what is the best importance distribution to pick, but really my ability to pick this Q is really limited by, is this a distribution I can easily sample from, right? So that's the thing, is I really, the thing with Q is I'm kind of tied to the fact that it must be a distribution that I can sample from. And like I said, there's not that many distribution for which we can easily sample from. So there could be, even though I'm doing this weight, there could be this problem where I generate a lot of samples under Q, right? I generate a lot of samples which are, let me draw this. Okay, so say here, which are highly probable, right? So highly probable under Q, but very unlikely under P, right? So because I'm still generating samples from Q, so I could be generating, so say 100,000 samples, but say, I don't know, 10,000 of them are unlikely under P. So the more likely under Q, but unlikely under P. So, but then the problem is when I do this weight calculation, I still have to compute the weights, basically. right? Because I generated all these particles under Q. So I still have to compute the weight. So while it's true that the weights will be small, right? Because the weight is P over Q. So if it's small under the target distribution, the weight itself should be very small. So while it's true that for all those particles the weight is small, I still have to do this computation, like say 10,000 times, right? So okay, so 10,000 is probably a small number. So suppose you have to do that computation a million times. But basically the idea is that it takes time to do all these computations, and then at the end of the day, it turns out that these computations are kind of useless because the weights are small, right? And if you also with small numbers, you start getting into numerical inaccuracies and so forth. So basically, we kind of want to avoid this. So this problem is called particle degeneracy. I think it's over. Yeah. So basically, is that many particles may have weights close to zero because they're highly probable under Q, but very unlikely under P. Right? So they're basically a waste. So what we can do is, so people try to think of ways to get around this, right? It's a real problem, but again, there's no perfect answer to this problem. So people start coming up with heuristics, right? Heuristics means it's a recipe, it's a method, it's a thing that we do, but it's not provably optimal. Whereas if you read something about LMS, like the stuff we talked about before, some of the things that like the algorithm suggests we do is provably optimal. But a heuristic, as soon as we start moving into Monte Carlo, many of the things we do are just heuristics in that people have shown with experiments, with experience that this is something you should do, but mathematically we cannot prove that this is optimal. But basically to get around this particle degeneracy problem, what we come up with is this heuristic, which is called the sampling importance resampling method. And the heuristic part is this resampling part. So we're still going to do importance sampling, but we're going to do an additional step, which is this resampling thing. And the idea of this is to try to reduce this particle degeneracy. So it's not, and also it's not just the fact that we have to compute all these excess weights. There's a lot of numerical inaccuracies that will result if you have these things around. So that's one thing. I don't want to, it's not just having to do with computation, but just think about the fact that we have this problem of particle degeneracy. Okay, so the idea is that we do two things. So this is still importance sampling, but now we have this additional step of resampling. So the first step is still the same. In that we still do, we still generate a fixed number of particles, or R particles, R trajectories from the importance distribution. And for each of these particles, we're going to compute their normalized weight. Right. And if you were doing normal importance sampling, you would just take this weight and compute the weighted average, and then you would be done. But when it comes to this sampling importance resampling, we have a second step. So the second step is the resampling. So the second step is you have, let's see. Right, so you have these capital R total trajectories. Right, and each one of them have a normalized weight associated. So now what you're going to do is you're going to now pick capital M trajectories from these capital R trajectories. So M can be a number greater than or equal to R. It cannot be greater, but M can be, it could just be equal to R. So if I have 5 trajectories, I could pick 5 points, right? But what is special is the way you pick these points. So you pick the point, you pick the samples according to their normalized weight. Right. So think of these normalized weights as a probability of picking the sample. So if the normalized weight of the first one is 0.1, then you have a probability of 0.1 of picking this one. If the probability of the second one is 0.95, then you have a probability of 0.95 of picking the second one. If the probability of the last one is 0.01, then you have a probability of 0.01 of picking this, right? So obviously, when you do this resampling, it's very likely that you pick this point, resample. So suppose M equals, so M equals to R. So if you keep picking R points again, it's very likely you keep picking this point, and then the next time, this point, and the next time, maybe this point, the next time, maybe this point, right? So when you see that when you start using this resampling idea, you very quickly start discarding the trajectories with the low normalized weights. Right, but that's fine, because those weights are, again, it's okay to discard these because these trajectories are very unlikely under the target distribution, which is what we're interested in, right? So after you do this resampling method, then you can go and estimate your expectation with these weights. Right. So now you can still apply the same importance sampling equation, but after you do the resampling step. So there is, of course, because it's a heuristic, there is also, you can see that you might end up with a case that supposes that this particle has 0.0 probability of 0.01, 0.95, 0.02, 0.001, 0.1. So you can see that if I want to resample this thing, like say 5 times, it might be that I end up with the second trajectory all 5 times, right? So that is, of course, also not desirable, because that means that the conditional expectation we're going to get is going to be this trajectory. But most likely this doesn't happen. But basically, if you overdo this, you can end up with another problem, which is not the same as particle degeneracy, right? So, but heuristics, right? What can you do? If it works, it works. If you're lucky, you're lucky. But yeah, so that's the idea. It's a very simple idea, is that you don't just stop with importance sampling. You do this one additional step where you do resampling. And again, you could resample the same number of trajectories, or you could resample a smaller number of trajectories. And then once you resample these, you take your resampled set of trajectories, and then you compute the average, the weighted average. Okay. I had a picture in the, let me see, in the lecture notes. So, no. right? So this picture is in the lecture notes. So yeah, so you can see that the target distribution is weird. So of course, what we want to do is we want to be able to use an importance distribution, which is a Gaussian, right? So when we sample from the Gaussian, obviously most of our samples comes from the higher probability region. So these are the size of the circle denotes how many samples we have in that region. So you see that this is when we sample from the Gaussian target, the importance distribution, we get these points. And the weight, so the size of the circle is associated with the normalized weight. So this trajectory has the highest weight, and this one has the lowest weight, right? So then when we resample, we're going to resample these particles according to their normalized weight. So that's why we have 6 particles here. We're going to still resample 6 times to obtain 6 new particles. And here, we're going to do it in such a way that this particle is drawn 3 times because it has higher normalized weights, and this particle is drawn 2 times, and this particle is drawn 1 time. So you can see that the makeup of the resampled particle set is not exactly the same as the original sample set, right? And then now what we do is we take the average of these particles, and this should give us a better estimate of the expectation of the target distribution than before. Right. Oh, also, I guess, sorry, what I meant is after you get the particles, you don't need to reweight them, right? Because the particles, the weight of the particles is already, the weight of the particle is already accounted for by the resampling step. So you see here, once you resample them, the size of the circle are all the same, right? Because when you resample this already accounts for the fact that these particles have higher probability. So you don't need to account for the size of the circle or the weight. Okay, so I think this is a good stopping point. But there's one problem with working with time series this way. And the problem is, this is the most intuitive when it comes to doing time series, but there's nothing in this, right, in this step that allows me to update with new observation. Right, everything we talked about here is if you have a time series up to time n, then I can tell you, I have a Monte Carlo method of computing the conditional expectation. But n has to be your final point. But then the question is, well, I'm working with a real-time system, the sensors are still taking measurements. So how do I deal with this when I start to get new data, right? Right, like what do I do with these new points? Do I have to now extend n to this new point and then recompute everything, right? It seems like that seemed like a really tediously bad idea and also extremely wasteful, right? So that's why this idea of just using the importance sampling on time series is not really used in practice. This is just an easy way for you to see the relationship between time series and importance sampling. But in practice, we cannot really use this because there's nothing in the classic method to update my estimation with new observation, right? Like we would with Kalman filters. So that's why on Wednesday, we will talk about sequential importance sampling. And this is what is truly, this is like common filters, where we update conditional expectation of xn. Right. So our belief of what the state is at time n probably depends somewhat on what the state is before, and also probably depends on what the observations are up to time n, right? So you see that this is probably the most general way of specifying what we know about the state of the system at time xn. Obviously, this is very difficult, so we have to make some assumptions at some point. But the idea is that what we need is a method which will allow me to update my estimate from that stuff, from time xn minus 1 to time n, right? So I need a sequential method. I can't, the way classic importance sampling work is not a sequential method. We need a way that can allow me to update in real time with new observations. Right. And that is called sequential importance sampling or particle filters. And like importance sampling, we will have to talk about weights. So there's the idea of normalized weights. And there's the idea of this resampling method. But the algorithm themselves, it's like a recipe. It's not that difficult. But to get a sense of where the algorithm comes from, there's a lot more, there's going to be a lot of mathematics of where the algorithms come from. And the reason is because we still have to compute these weights, but now we have to do it in such a way that this thing is updated sequentially. So meaning that we cannot keep this as just a complicated looking probability distribution of these sequences. We have to use Bayes' rule and start looking at them as products of things and so forth, right? So, but we'll talk about that on Wednesday because we don't exactly have time right now, right? And because we're going to break this complicated probability distribution via Bayes' rule, we're going to start making assumptions so we can get rid of some terms, right? So the notation becomes tedious, but the basic idea is very much the same. Okay, so any questions? It would be better if you guys don't type in chat. It would be preferred if you verbally write something. Okay, so any questions? Can you hear me? No question. Okay.
Yes,
well,
yes, we can hear you.
Okay, so if there's no question, so does the latency on the whiteboard bother anyone?
No, it's okay.
Okay. So I think on Wednesday I'll try a slightly different method just to compare, and then you can tell me which one you prefer. From my end, I have to remind myself that you can't actually see when I tap on a part of the whiteboard, except when I'm using this cursor laser pointer thing. But it gets it's hard to remember. Okay, so then if there's no questions, then we can go. Just in class a bit early. Okay, yeah. So email me if you have any questions about the homework. I'll still have office hour, quote unquote, on this chat, in this room at the same time. And if you need some outside help, you can email me and we can schedule something or something. Okay. Okay. Well, then if everything's good, then I'll close the meeting and I'll stop recording somehow. Okay. So, okay. See you guys.
Okay, thank you.
Bye.